All right, the car through a gully question. I've been asking this question in one form or another for years. It's actually a bad question. I'll show you why in a sec. A couple things that make me laugh about it is people didn't know what a gully was. So a gully, I put it in quotations there. I thought it was a word that everybody knew. A gully, when I type it, meant like a half pipe. That might be a word that would be used in your vernacular. So just a semicircle thing. We got a car going 72, which, excuse me, which as you'll see is, that's part of the ridiculousness of the question. That's a little bit fast. So I'm curious about when our car's at the bottom. As it zooms up and out of that hill, I'm curious to know what the normal force on the car is at the bottom of that gully. As always, we're going to draw a free body diagram. Normal force up, gravity down. Whenever anything's going in a circle, it turns into an F net equals ma situation. The A becomes v squared over r, and then we just have to think about the tug of war of forces. This is another vertical circle, so I've got to deal with gravity. In this case, it's normal and gravity. They're in a tug of war. It's almost as if we've got a person on an elevator that's accelerating up really quickly. Since they're accelerating up, the upward force has to overpower the downward. So I'm going to say that normal minus gravity is equal to mv squared over r. That's my tug of war. The way this one's worded, I'm curious about the normal force. If I flip-flop things around, that's mv squared plus mg. Subbing in what I know into this terrible question, the mass I made up was 1500. Converted over, the v is 20, and then the radius is a very small 10. And then to that we need to add our 1500 times 9.8. When you crank that out, we are going to get the ridiculous number of 74,700 newtons. In hindsight, I haven't changed the question because I kind of like it because it's so ridiculous. You're going way too fast for that sharp of a curve. But we can work off of this. Think back to the boring case. If this was a boring case, the norm would be equal to gravity. That's equal to mg. We would get a force of, normal force would be like 14,000. That's what you feel. Sorry, the normal force is what you feel. So if it's a boring case, if you're just sitting in your car at a red light, the normal force on your car would feel like it had a weight of 14,700. If you're in your car and you're flying at 20 meters per second through a 10-meter half pipe, you're going to feel, the normal force on the car is going to feel like a weight of 74,700. If we do a quick little ratio, 74,700 divided by 14,700, it's almost exactly 5. So another way to think about this is you would feel 5 times larger than your regular weight if you're going through the bottom of the circle. That's kind of ridiculous. I think if you Google it, jet pilots that are training in the Army, they start passing out at 3 times the regular weight or at 3 accelerations. So if you're going 5 times, if the normal's 5 times bigger than normal, if the normal's 5 times bigger than the boring case, you would probably pass out. Your car would probably snap in half. You'd bottom out your shocks. Something would probably break. So from that perspective, the numbers are ridiculous. But from something that we can use going forward, is the normal force that we calculate is really what you feel. If I told you you felt 5 times your regular weight, then we would know that the normal is 5 times the boring case normal. If you feel half your normal weight, then the normal force in that situation would be half of the boring case. So we can use that, and that's kind of a common way questions are framed when we talk about things going in vertical circles. How heavy